Welcome to The Explainer. Today we're diving into something that powers literally everything, our whole world. But you can't see it, you can't touch it, and you definitely can't hold it. We're going to break down the fundamental nature of energy itself.
So let's just jump right in with a question. You've got the sun, this giant star, right? And then you've got a log of wood. They seem about as different as you can get, but they actually share something absolutely profound. Any ideas? And the answer, of course, is energy. Both of them are just these incredible vessels of potential energy, basically waiting to be let out. Now, the sun's energy is locked up in its core through nuclear fusion, while the log's energy is stored in its chemical bonds. It's the same fundamental physics, just on completely different mind-boggling scales.
So that's our journey for this explainer. We're going to explore these fundamental types of energy, from the light you can see to the power in chemicals, all the way down to the insane force that's locked up inside a single atom.
Okay, first up, let's start with the one form of energy we deal with every single day, light. But as this slide hints, what our eyes can actually see, it's just a tiny, tiny piece of the whole story.
Yeah, the light that comes from the sun is just one small slice of this huge energy field. Think of it like a wave, an oscillation just moving through space. And this electromagnetic field is all around you, all the time. It's the radio waves bringing you music, the microwaves cooking your lunch, and the light coming from this screen right now.
And here it is, the whole electromagnetic spectrum laid out. Just look at that. You can see radio waves on one end, all long and stretched out, and gamma rays on the other, super short. Now look for visible light. See that tiny little band in the middle? That's it. That's everything the human eye can see. The rest is totally invisible to us.
This really shows you the fundamental trade-off here. It's all about a wave's length versus its frequency. You've got these long, kind of lazy radio waves that have a low frequency. But as the waves get shorter and more bunched up, like with X-rays, their frequency, how many waves pass by every second, just goes through the roof. It's a simple seesaw. One goes up, the other goes down.
So why does that relationship matter so much? Well, it's because this energy travels in these little packets called photons. And here's the kicker. A photon's energy is tied directly to its frequency. So a high-frequency gamma-ray photon is packing way more punch than a low-frequency radio wave photon. And that, right there, is why some radiation is harmless and some is really dangerous.
Okay, let's shift gears. We've talked about energy that travels through space. Now let's talk about energy that's stored inside matter itself. This is where we get into the power of chemistry.
The best way to picture chemical energy is to think of the bonds holding atoms together like tiny coiled springs. Seriously, these little springs are holding molecules together, and just like a real spring, there's a bunch of potential energy just waiting inside. So when you break those bonds or form new ones, you can release that energy. And burning something, combustion, is the perfect example. When you burn natural gas, you're not actually creating energy. All you're doing is rearranging atoms. It takes a little bit of energy to snap the old bonds apart, sure, but when the new, more stable bonds form to make CO2 and water, they release way more energy. And that extra bit that's released, that's the fire. That's the heat and light we feel.
So what even is that heat? Well, what we feel is just the big picture effect of that energy release. Down at the molecular level, all those new CO2 and water molecules are just moving and vibrating like crazy. So heat is really just the collective motion of trillions of these supercharged molecules bumping into everything in their path.
Okay, we've gone from waves in space to the bonds between atoms. Now we're going even deeper, right into the heart of the atom itself, the nucleus. And this is where we find the most powerful forces in the entire universe.
So there are basically two ways to unlock this insane nuclear energy. The first is fission. That's where you take a really heavy, unstable nucleus like uranium and you split it apart. This is how all our current nuclear power plants work. The second is fusion, which is the opposite. You take two really light nuclei, like hydrogen, and you smash them together to make a heavier one.
And this brings us full circle, right back to the sun. Fusion is the engine of the entire cosmos. All the heat, all the light that reaches us here on Earth, the very energy that powers almost all life, it's all the end product of a massive, constant nuclear fusion reaction that's happening 93 million miles away. It's incredible when you think about it.
So we've got these amazing primary sources of energy, right? But how do we turn all that raw potential into something useful? I mean, how do we get it to actually power our lives? Well, that's where we start harnessing motion.
This is mechanical energy. It's the energy of motion, which we call kinetic, and the energy of position, which is potential. Just think about flowing water in a river, the wind turning a windmill, or even a simple compressed spring. It's the energy we use to physically move things around and get work done.
And that leads us to electricity, which is the ultimate utility player. I mean, electricity isn't really a primary source of energy, it's more like an energy carrier. Its magic is that we can move it super easily over huge distances and then convert it into pretty much any other form we need. Light, heat, motion, you name it. This energy conversion chain is pretty much how we generate most of our power today. It's a beautiful process. You start with a source fuel, like the chemical energy in coal or the nuclear energy in uranium. You convert that to heat, thermal energy. That heat boils water to make steam, which creates mechanical energy by spinning a massive turbine. And finally, that spinning turbine turns a generator, which converts the motion into electrical energy.
And this gets us to the single most important takeaway of all this. Energy is never created or destroyed. It's just converted from one form to another. From the fusion happening in the sun, to the chemical energy in that log of wood, to the electricity powering your screen right now, it's all part of one grand, interconnected system of transformation.
So, you see, understanding these fundamentals isn't just for a physics class. It's the key to everything about our future. The real question for all of us is, which of these energy conversions are we going to bet on? Are we going to stick with combustion, find better ways to turn solar radiation directly into electricity, or maybe, just maybe, finally master the fusion that powers the stars? The answer to that is going to define our world for generations.